In section 6.2, we're going to start taking a look at discontinuous functions. And that may seem very strange because we're looking at differential equations. And I know that if a function isn't continuous, it's also not differentiable. And if the derivative doesn't exist, it can't be the solution to a differential equation. But generally speaking, we're going to be looking at something that's discontinuous just at a single point. So the derivative is going to fail to exist at that point. But we'll know what the derivative is to the left of that point. We'll know what the derivative is to the right of that point. And often we'll have enough information to know that we want the two pieces to fit together to give us a continuous function. And so we'll still be able to solve things. Now, if I wanted to do this without Laplace transforms, I would have to just define all of my functions piecewise. And for each piece, I would have to solve a separate differential equation. Laplace transforms is going to allow us to deal with discontinuous functions all at the same time without having to break them up into pieces. So the first function I want to look at is the Heaviside function. It's actually a family of functions, mu sub a of t, where a is just going to be some real number. It's defined piecewise. It's 0 if t is smaller than a, and it's 1 if t is bigger than or equal to a. So the graph of it looks like this. To the left of a, the graph is just at 0, so it's along the t-axis. At a, it jumps up to a height of 1, and then it stays constant at 1 forever and ever and ever. Okay. Now, because with Laplace transforms, I only care about functions from 0 on. If I were to use the Heaviside function for a negative value of a, that would be equivalent to just looking at the constant function 1. So we're going to be looking at the Heaviside function where a is bigger than or equal to 0, and where it's bigger than 0 is really going to be the interesting case, because if a is 0, it's just the constant function 1. Okay. Where this is useful is I can sort of think of this as an on switch. Let's just take a look. If I had mu sub pi over 2 of t, and I multiplied that by sine of t, that's going to be a piecewise function. If t is smaller than pi over 2, I'm getting 0 times sine t, which is just 0. But once t is bigger than or equal to pi over 2, I'm getting 1 times sine t, so I'm just getting sine t. So if I take a look at what that would look like, here's pi over 2. To the left of that, the function is turned off. I'm just getting 0. At pi over 2, the sine function suddenly turns on. Sine of pi over 2 is 1, and so now I've suddenly got my sine function. Okay. And then it continues on forever and ever and ever. So I can think of mu sub a of t as being sort of like an on switch. Turns a function on. I can also use the Heaviside function to turn a function off. So if I look at 1 minus mu sub a of t, that's going to be an off switch for me. Let's just take a look. Let's suppose I wanted to look at 1 minus mu sub 2 of t times t squared. So if t is smaller than 0, mu sub 2 of t, if t is smaller than 2, mu sub 2 of t would be 0. So I've got 1 minus 0 is 1 times t squared is t squared. But once t is bigger than or equal to 2, the Heaviside function is 1. 1 minus 1 is 0. 0 copies of t squared is 0. So what this would look like is I would have the function t squared until we hit 2, at which point it would jump down to 0, and so we've turned the function off. Okay, kind of neat. Okay. One place where we've talked about the Heaviside function previously, although I don't think I called it by that name, is we mentioned that with Laplace transforms and inverse Laplace transforms. Okay. Because Laplace transforms are just applied to functions defined from t equals 0 to infinity. If I were to take the inverse Laplace transform of something, and it gave me something like this, the inverse Laplace transform is one-to-one. It's going to give me this and only this on the interval from 0 to t. But there could be infinitely many different functions defined on the entire real number line that match this function on the interval from 0 to t. So if I want my inverse Laplace transforms to give me a unique function defined on the entire real number line, what I can do is simply define them to be mu sub 0 of t times f of t. So that essentially my function is turned off until time 0, and then I get the inverse Laplace transform. Okay, so I want to take a look now at what happens if I take the Laplace transform of the Heaviside function. And we are assuming here that a is going to be bigger than or equal to 0, because, again, because Laplace transforms only care about things from 0 on. If I turn something on at a negative time, it's just on the entire time from 0 to infinity. Okay. So according to my definition, that's the integral from 0 to infinity of mu sub a of t times e to the negative st dt. Now what I'm going to do is just break that up into two integrals. That's the integral from 0 to a of mu sub a of t times e to the negative st dt, plus the integral from a to infinity of mu sub a of t times e to the negative st dt. Now, over the interval from 0 to a, my function is 0 almost the entire time. At a, that's essentially where we're turning on e to the negative st, and so my function would jump up at that one point to take on that positive value. Okay. So the function I'm integrating is actually discontinuous. That's okay. Integrals are defined as limits of Riemann sums. And way back when we first learned what an integral was, even though we almost always work with continuous integrands, we learned, at least I hope we did, that if the integrand has a finite number of discontinuities, the function is still integrable. It can even have infinitely many, but it gets a little bit more complicated to say what the conditions are there. But if I've only got finitely many discontinuities, and here I have one is a finite number, okay, it's going to be integrable. Because if you think about it, if I created a Riemann sum here, all but at most one of my rectangles would have a height of 0. And because when I take a Riemann sum, I'm shrinking the base of those rectangles to 0, even if I always chose this as my representative point to get a rectangle with this height, its base is going to be shrinking to 0. So I'm just going to get 0 for this integral. And then this integral, from a to infinity, this is just 1. So here I'm just integrating e to the negative st. So I'm going to just write that as the limit as b goes to infinity of the integral from a to b of e to the negative st dt. Now I'm going to evaluate that with my nifty u sub. We'll let u equal negative st. So then du is negative s dt. So if this is going to work, I'm going to need to introduce a negative s, which would mean I'd counterbalance with a negative 1 over s. Now obviously that would be undefined if s is 0. Can s be 0? No. Because if s was 0, this would just be e to the 0. What I'd be integrating is a constant function of 1 from a on, from a to infinity. But that would give me infinity. The integral would diverge. So I know that s can't be 0. Okay. So I'm able to do this u sub. Now, the reason that s can't be 0 isn't that, well, if it were, my u sub wouldn't work. That just says I can't use that technique if s is 0, but because I get a divergent integral. Okay. All right, so this becomes the limit as b goes to infinity of negative 1 over s, integral from the u value at a, which would be negative s times a, to the u value at b, oh dear, I'm running out of space here, yeah, I'll just erase that. To the u value at b, which is negative s times b, e to the u du. So, let's come over here to finish that up. That's going to be the limit as b goes to infinity of negative 1 over s e to the u evaluated between negative sa and negative sb. So that's the limit as b goes to infinity of negative 1 over s times e to the negative sb minus e to the negative sa. Now, this is the only part that has a b in it. I'm hoping that this is going to converge. We already said s can't be 0. If s was negative, this would become e to a big positive power. That would go off to infinity, my whole integral would diverge. But if s is positive, this is e to a big negative power, and that's going to go to 0. But only if s is positive. So in order to get a convergent integral here, we have this restriction that s has to be positive. Okay. But then, I'm just going to get negative 1 over s times negative e to the negative sa. That's, the two negatives will cancel, e to the negative sa, over s. Okay. So, we've got this lovely formula that the Laplace transform of the Heaviside function is e to the negative sa all over s, with the restriction that s is bigger than 0. And of course, we did specify that we want our a to also be bigger than or equal to 0. I do just want to take a look really quickly at if I were to take a look at the Heaviside function at 0. That's equivalent to just taking the Laplace transform of 1. Because remember, with Laplace transforms, we're only looking at what happens from 0 to infinity, and this turns on at 0, so it's 1 the entire time. Now, if I just plug into this function, I'm going to get 1 over s, because I'd be plugging in 0 for my a, so I'd get e to the 0 over s, which is 1 over s. Now, that's consistent with what we've seen before, because we also said we could write 1 as e to the 0t. And then if I used the formula for the Laplace transform for an exponential function, I would get 1 over s minus 0. So that's kind of neat that we can see we can calculate this a couple of different ways, and the rules are consistent with each